the multilayer feed-forward neural network. In parentheses, multilayer feed-forward neural network. I put those in parentheses because, they technically describe, the specific kind of neural network we're talking about, but typically we just say neural network. Okay, so, the input, that's fixed by the problem. Okay, so let's assume that we're in D dimensions. So the input is this augmented input. Okay, so the input is 1, x1, x2, all the way to xd. Okay, now it's cascaded perceptrons. That's the multilayer perceptron. Okay, except that so in each layer we can have something like a perceptron, except that it's no longer going to be the sign. It's going to be a sigmoid. Okay, to make it softer, more manageable, basically differentiable, so that we can run gradient descent. Okay, so you have, let's say this is layer 1. Okay, so you have your vertices, your nodes. Okay, then you can have layer 2, and you can have your nodes. Okay, and then we can have layer 3. Okay, and I'll just illustrate with just one extra layer here. Okay, so imagine that we're using 3 layers. So this last layer is called the output layer. So this is the output, h of x. Okay, and so what's going on? You're basically implementing perceptrons. So you can imagine that here I have one perceptron, put it in blue. Okay, and here I have another perceptron. I'll put it in red. Okay, so remember there are weights, and you add up the inputs, you multiply each input by the weights, add up and feed it in here. And I'll put this, third guy perceptron here, green. Okay, so inside here used to be the sign, but now we're going to put a sigmoid, so I'll call it theta. Okay, and then we have sigmoids in here. You can imagine that we can also have the sigmoid in here. Okay, and again we are implementing perceptrons. Okay, so we have a perceptron here. We have another perceptron here. Well, it's like a perceptron because it's not quite a perceptron because that we're not taking the sign of the output. And the final perceptron here. Okay, and we have this third layer. Okay, we could keep on adding layers if we wanted to. Okay, and here if this is indeed the output layer, we just have one perceptron, one linear model, okay, but with the tanh. Okay, so I'll put this in black because it's the final layer. And so there's just one output. So let us say that we have layers. So we have layers, and we'll use L to represent the layers. So you have layer 0, and the final layer is, we'll call it layer L. So here we have layer 0, layer 1, layer 2, layer 3, and in this case, big L equals 3. So that's the final layer. Now, if we wanted to refer to a node in this network, okay, if we wanted to refer to a node in this network, we will observe that the node can be specified by telling me what's its layer, okay, and in this layer, what position does it occupy. So a typical node will have, a representation as a layer, and we'll typically use superscript L for layers, okay, and its position within the layer, so I'll call this I. So this is, node I in layer L. Okay, and so if we want to refer to a quantity, but particular to a particular, that's let's say the input to this node, or for example the output to this output of this node, we could talk about the input, Li. That's the input to node I in layer L, or the output Li. That would be the output of a node in layer L at position I. Okay, and these guys here. So this is called the output layer. So this is called the output layer. And this is called here the input layer. Okay, no surprises there. And in between here are what are called hidden layers. And in this particular example, we have 2 hidden layers. Okay. Now, remember what I told you. We get to specify the weights on each of the edges. Okay. Now, what do I mean by... So multi-layer is kind of self-evident. We have multiple layers. What do we mean by feed forward? What we mean by feed forward is that, once you tell me the inputs, those feed forward to the next layer. And then those feed forward. The outputs of this layer feed into the next layer. And the outputs of this layer feed into the next layer. You don't have, outputs, going backwards. So the outputs of this layer do not feed into the inputs of this layer. That would become a recurrent neural network, much more complicated, okay, not within the scope of this course. Okay. Now, in theory, you could still remain feed forward and have the output of this layer, feeding into the input of that layer. So you could have an edge going this way. We're not going to have those edges. It would still be feed forward. Okay. Basically, if you think of this as a graph, and if the edges had arrows, all the arrows would be pointing from left to right. Okay. And then we could immediately say that this graph has a topological sort. So as long as the graph has a topological sort, you could think of it as feed forward. But let's simplify. So this is layered, sometimes called leveled. So it's a leveled network, and it's feeding forward. So the inputs feed from the left to the right in the typical way we draw it. Okay. Now let's drill down into a single node. Okay. So you have a typical node in your network. In your neural network, so let's call this node in layer L, and it's node I. Okay. And, it has some output. There's an output, and there's an input to this node. Okay. Now, what we will do is we will call this input the signal coming into this node. So this is the input. Okay, and we'll call this the signal SLI. So the signal that's coming into the node. And then there's an output. Okay. Output. And we will call this XLI. So the output of layer 0 is X0I, okay, which correspond to the features for your input example, let's say. Okay. And the output is related to the input by this transform theta. So the most popular choice for this transform, or a popular choice nowadays, there are competing choices, but the one we will use is a standard sigmoid. So theta of S, goes from, it's approximating the sign, so this is +1, this is -1, and so this is S, and so this is theta of S, the sigmoid. And a very popular choice is equal to tan H of S, the hyperbolic tangent. So tan H of S, this is the sigmoid, okay, that we will pretty much be focusing on. So you have an input to a node, and then its output, and these are related by X, L, I is equal to theta of S, L, I. Okay, so there's no rocket science here. Now, the interesting part in the neural network is, okay, how is the input constructed, and what is done with the output? Okay, you have an input and an output. Okay, so that's the output and the input. Now, what's happening to get the input? So let's take this guy, for example, this node. Okay, from the previous layer, or even this node, from the previous layer, you take all the vertices, all the nodes in the previous layer, and you're computing a perceptron. Okay, so there's a perceptron coming in here. Okay, so there are edges coming in. Okay, they all come in, okay, and from the various nodes in the previous layer, and we add, okay, and that's what gives us the input. Okay, so you can think of a weight coming in from the previous layer to the current layer. So we will call this weight WLJI. So this is node I. So from the previous layer, node J, to the current layer, node I, WLJI. Okay. And in fact, what's going on is that these you could summarize the weights coming into this guy as just a perceptron. So we could call that little WLI if we wanted to. So there's a perceptron coming into this node here. Okay. Now what about going out? So let's look at what's going out here. Well, there's an edge, there's a weight going out to every node in the next layer except to the augmented one. Okay. So if you think about it, okay, so there's a node, there's an edge going out to every node in the next layer. Okay. And so we will, so since the weights coming into this, the edge weights coming into this node were WL, so these weights are WL plus 1, okay, and they're going from I, let's say, to K, from I to k. So the weights going into layer L plus 1 from node I to node k. Okay. Now, let's think about what's going on in this next layer if we're focusing on, let's say, this node. So let's say we're focusing on this node. Okay, so what's going on in this layer is its weight comes in, there's another weight coming in, there's another weight coming in, another weight coming in. All these blue weights form a perceptron into this layer. Okay. Now, it's convenient to represent all these perceptrons that are coming into this layer as, perceptron weights W1, perceptron weights W2, perceptron weights W3, and so on. So this matrix of weights, there are many weights in here, but it's composed of a set of perceptron weights W1, set of perceptron weights W2, set of perceptron weights W3, and so on, depending on how many vertices. So it's convenient to represent this set of weights WL as, the weights coming into vertex 1, node 1, so WL1, WL2, and so on. Okay, so this is WL. These are column vectors. Okay, but now how many are there going to be? Okay, so we're going to define the dimension of layer L. So the dimension of layer L is going to be DL. Okay, so you can think of this as node 0, the augmented 0, node 1, 2, 3, so node 1, node 2, node 3, and so on, up to D1. Node 0, 1, 2, and so on, up to D2. Okay? And then, the dimension of layer 0, the input layer is going to be D0, which is actually just the input dimension D. Okay? So how many perceptron weights are coming into layer L? WL1, WL2, up to WLDL. So that's the number of perceptron weights coming in to layer L. Okay. And each of these, so the perceptron weights that are coming into node I are WLI, which are part of this big matrix of weights. It's convenient to store all the weights coming into layer L as a matrix of weights. Okay. And then, similarly, okay, we can store this as a matrix of weights. WL plus 1 is equal to WL plus 1, 1, okay, WL plus 1, 2, and so on, up to WL plus 1. Okay. So the weights going into layer WL plus 1 will have, there'll be dimension DL plus 1. Okay. So, just so that you have some practice with this notation, exercise. What are the dimensions of WL and the weight matrix WL plus 1? Okay. What are the dimensions of the weight matrix WL and the weight matrix WL plus 1? Exercise. Okay, now let's look at the inputs and the outputs of the nodes. So the inputs of the nodes, so there's an input to node 1, there's an input to node 2, there's an input to node 3, and so on. How many inputs are there? DL, if we're talking about layer L. So we can construct a vector. It's convenient to construct a vector in SL, the input vector. Okay, so the input vector SL, okay, which contains the input to node 1 in the layer, the input to node 2 in the layer, and so on, the input to node what? DL. Okay, so a vector of all the inputs. So this here, the vector of all these inputs. So this vector coming in here would be the vector of inputs S into layer 1, S into layer 2. Okay? And the whole set of outputs, okay, X out of layer 1, X out of layer 2. So XL, okay, the vector of outputs from layer 1 is, okay, now we have the augmented one, and then XL1, and so on up to XL, DL. Okay. So this is just some notation. Okay. So going into layer L is a matrix of weights, a vector of inputs, one for each node in the layer, okay, a vector of outputs, and then a matrix of weights connecting the layer L to layer L plus 1. Okay. Okay, so this is the neural network in terms of notation. Let me show you a slide, okay, with a nice clean summary of all this notation, okay, and then we'll call it quits. Okay, so we can see here the nice neural network in all its glory, okay, and let's drill down into a single node and all the details that we just discussed. Okay, there are the inputs to the layer, which is the vector SL, the outputs of the layer, which is the vector XL, okay, and the weights WL, the weight matrix WL connects layer L minus 1 to layer L, and the weight matrix WL plus 1 connects layer L to layer L plus 1. Okay, so on the top right, you can see the neural network, again, in all of its glory, and drilling down a little bit of the detail of what's going on at a particular node. And let me end by showing you now what we started with, the biological inspiration, and then what we ended with, the neural network, the thing that, you know, accomplishes the engineering success, that gets us the performance we want in predicting for out of sample. Okay, so on the right, biological inspiration, the neural network in your brain, okay? And on the left, the neural network that, you know, we use in order to engineer a model that predicts from, you know, input X to a prediction H of X, and hopefully we can get this thing to perform well out of sample. And we've seen in practice that, you know, it can work very well. So checking out for now. See you next time.